Okay, we are going through the procedure for calculating signal timing. We started with one example. Okay, so okay, this was intersection which was given. Okay, the lane data was given. For every movement, you have the volume, some of the other characteristics. Okay, and the speed is given. The first thing we need to decide is if the left turns are protected or permitted. Okay, in this case they were protected because of the speed. Okay, speed is 45 miles per hour or more, you have to make it protected. Okay, which was the case here. So this thing is done. Second thing is you have to identify the lane groups. Okay, lane groups are lanes which are having same movement. Okay, so if you look at the geometry of the intersection, none of these lanes have the same movement exactly. So all of them have to be in a different group. Okay, so 3 here, 3 here, 2 here, 2 here. Okay, then for each lane group I should have the flow. Okay, so the movements are given here. Now for this group, this one left turning groups is very easy because it's only one movement, right? So you just put the left turning movement with the group. Okay, for the straight we have 2 lanes. Okay, in each direction we have 2 lanes for straight. You can go from here or here. Okay, so we have to divide the flow. Okay, and we said we don't have equal distribution. Okay, we have unequal distribution, especially because this one is also for the right turning. Okay, so this lane group will have 55% of the straight, and this one will have 45% of the straight plus the right. Okay, same thing on the other side. And for this one, very easy, straight and right both. Right? There is no division here. Okay, so you distribute the demand and then you divide the demand with peak hour factor. Okay, so that it becomes flow rate. Okay, all the calculation is done on the basis of flow rate. So you have to convert it to flow rate. So all the values which we discussed must be converted to flow rates. Okay, so we divide by peak hour factor. That's very easy. Another factor which we did not use here was what? Heavy vehicle factor, because there was 0% heavy vehicles, so did not use it. But if they are there, then all of the flow rates must be divided by the heavy vehicle factor to convert to passenger cars. Okay, because capacity, saturation, fluid, everything is in passenger cars. Okay, so once you divided the flow for each lane group and you converted it to flow rate and you converted it to passenger cars, then you take the ratio of the demand with the saturation flow rate. Okay, so these are the saturation flow rates for each lane group. In this question they are given. How to calculate it? You have to go back. Okay, like to high school or something, because we already covered it. Okay, so here they are given. So divide the flow rate with the saturation flow rate. Okay, and you will get a ratio which obviously would be less than 1. Yes.
About this important demand divided by VHF, how we get it?
Demand divided by the
second table.
Which second?
158,369. It's different.
They are different because these are total for each movement. They are for each lane group. So northbound 2, which one is northbound 2? Northbound 2 has straight and right both, right? So this is straight right both.
And about percent 55 and 45.
That only happens here. East and west. Yes. Where do you have shared movement? Do you have shared movement here? Any movement shared? No. Okay. There are they're stable according to movement. They're stable according to lane groups. Okay. Clear? They are the movement and they are the lane group. They are not the same. Okay. Clear or not? Any question? This means what? Question.
No, I get it.
Very good.
No complexity.
Explain to him. Huh?
No complexity.
No complexity. See, if this question comes in the exam, it's because of it. Okay. So we did it up till here. I asked you to do the summation of all these V by S ratios. It was more than 1. Okay, and this is where we stopped. We said that now the next step is to make the phases. Okay, design the phases of the signal. Okay, the easiest strategy is give each phase to each lane group. So one phase for this one for this one for this one for this one. Okay, this is the easiest thing to do. Okay, but this means what? When you did the summation of V by S ratio, it was more than 1, right? If you give one phase for each movement, in the end you need, your flow rate is more than the total saturation flow rate. Okay, so this is not possible. Okay, if you have a problem in which you do the summation of V by S and it is 0.8, 0.9, that means even if you give a phase for each lane group separately, it is still workable. You can still do it. Okay, but in this case it's not happening. It was 1.71. Okay, so if I give a phase for every movement, a separate phase for every movement, my flow rate is more than the total saturation flow rate. So this cannot work. Okay, so now I need to do what? I need to do some overlapping. Some of the movements should happen in the same phase. Okay, and this is where you can use your judgment. This is where you can play, okay, with the phasing diagram. Okay, this is what we call as a ring diagram. Okay, the phases of the signals are normally shown in this way. Okay, so you see boxes, okay, and then they have shown the movement on top of the, okay, which road they are talking about, east, west, north, south, and each box shows a movement from one direction. Okay, so this one shows the eastbound movement, left turning. This one shows eastbound movement, straight and right. Okay, and so on and so forth. Boxes are together, that means these movements are happening simultaneously. Okay, so if you look at this phasing, again, they have again taken the easier approach, which is what? Give one phase for each direction, and when it becomes green for that direction, all movements from that direction will go together, whether they are left turning or straight or right turning. Okay, so one phase for eastbound, one phase for leftbound, one phase for northbound, one phase for southbound. Okay, clear? So you see these two movements overlapping, these lane groups overlapping, these lane groups overlapping, these lane groups overlapping. Okay, there. Now look here. Is this one lane group or two? Two, right? So this one has its own V by S ratio, this one has its own V by S ratio. Which one is 0.27? Both of them have the same in this case. Okay, let me take another example. No, I cannot. There's no other example. Anyways, if but they are already separate meters. All written like this. Anyways, let's say this one was 0.29, this one was 0.27. Okay, so which one you will take? 0.29, the one which is higher. Okay, so if you have two lane groups in the same phase, you will take the higher one. Clear? Clear? So this phase will be designed for which one? 0.27. This one will be designed for which one? 0.17. This one will be designed for which one? 0.19. Okay, and so on. Clear? Whenever you have multiple lane groups in the same phase, you will take the one which has higher V by S ratio. Clear? Okay. Now, so these two, I am designing for 0.27. So I don't have to worry about this one. I will only have this one. So this plus the next one, this next one, this next one, this. Now if I add these values together, I get the total sum to be 0.86. Okay, how much was it? 1.17 when I was giving every phase for every lane group. When I merged them together, when I did the overlapping, I reduced it from this to this. Okay, this is acceptable, no problem. Okay, this is acceptable. 0.86 is a very good value. This can be done. You can move forward. Okay, but some few points which you have to keep in mind. Obviously, you cannot do multiple examples. So you can see multiple trials. All these trials are acceptable. All these trials are acceptable. Okay, but let me tell you what they are doing. So now you see here in this one, they are merging two movements, two lane groups. This one requires 0.27. This one only needs how much? 0.19. Okay. Now if these two go together, what will happen? You are designing the time according to which one? This one, right? Okay. So that means you are giving extra time to this one for what? Nothing. Okay. And these are the same thing happens here. Okay. This one 0.09, this one 0.19. You are designing according to this one. So this one will have extra time for nothing. Okay. When we are talking about overlapping the movements, the more preferable approach is overlap those movements which have closer V by S ratio. Whose V by S ratio is closer to each other. Okay, for example, you see the second attempt here, second trial. Okay, so now 0.19 and 0.12. See? Okay, so instead of overlapping between straight and left, they are overlapping between two left turnings and two straights. Okay, and same thing here. Okay, so when they did this, what happened? 0.19, 0.12. So now much better than this one, right? It was 0.19, 0.27. Okay, this one was, now this one still you will deal with it later on. Okay, but this one become much closer. This one exactly same, and this one also closer. Okay, so now you see the movements which are happening together, their V by S ratios are much closer than the first attempt. Okay, now when you do the summation now, what happens? So again you will do the summation for the ones which is higher, right? So out of these two you will take this one, plus this one, plus this one, plus this one, the higher one in every case. Okay, but we change the arrangement now. Okay, so now the summation is 0.7. Okay, it was how much? Became better or not? This is an indication that we did something good. Okay, if you are trying different things and V by S ratio is decreasing, that means it's becoming more and more beneficial. Okay, it's becoming better. Clear? Okay, now one more thing which they did here. Okay, now you see here this one 0.17, this one 0.27. Okay, again the same problem will happen here. Okay, you are giving extra time to this movement for no reason. Okay, which one needs more time? This one. Okay, so can I extend this on this side? No, this is crossed, right? I cannot extend it. Can I extend this on this side? So this, okay, and which one? This and this one. Okay, if I extend this movement on this side, then I will have this one and this one together, right? Clear or not? If this movement is extended in this direction, so this one will remain 0.17. Okay, but this 0.27 will be somewhere here plus some part here as well. Is this possible? Yes. Okay, because this movement needs less time, right? This doesn't need more time. Okay, so I can squeeze this movement and extend this movement into this zone. Okay, so when this movement happens like this, so you need, now see, this one less, this one extended into the remaining time. Okay. So now what is happening? These two left turning will happen together for some time. Then what will happen? This left turning and this straight will happen together again. Possible. Both of them are eastbound, right? So this is also possible. So, and then you have the other straight. So these two straight happening together, no problem. Okay. Here they were already exactly same, and the difference is very low here. You see here, 0.19, 0.23. Difference is very low. I can do this here as well, but okay, it was more beneficial here than here. Okay, here the difference is 0.1. Here the difference is only 0.04. So we can leave it, but you can do it as well. No problem. Clear? Okay. You see what we did here. I had one movement here and one movement here. Both of them needed less time. And I have this movement which needs more time. Okay. So I extended the time of this movement by decreasing the time of the other movement. Okay. Clear? Now, how can I calculate the summation of V by S now? When I get this. Earlier, what was I doing? Out of these two, pick the higher one. These two, pick the higher one, right? Because they are happening together. Okay. But now what would I do here? Can I pick 0.19? Out of 0.12 and 0.19. Can I compare them together? No, because this one is already having less time. So I cannot compare these two together. I can only compare the V by S ratios together which are going in the same time. Okay. This one already has more time, this one has less time. Okay, so I cannot compare them directly now. So what do we do? You look at the entire combination. This is one combination and this is one combination. Why I am saying this is the combination? Because you see this one, they are conflicting, right? So this is one sequence. They have to happen in a sequence, right? They cannot happen together. So I will look at the sequence now. What is the sequence? 0.19, 0.17. How much? 0.19 plus 0.17, how much? 36. 36. And this is another sequence again. They are conflicting, so they have to happen one after the other. Okay? So if you go with this sequence, 0.12 and 0.27. How much? 0.39. Which sequence is higher? I'll take this one. Okay. So if you have something like this, then you can simply compare the V by S ratios with each other. Whichever one is higher, you will take. Okay, for your design. But when you have something like this, okay, where movements are, phases are overlapping and changing, okay, then you have to look at the sequence, the whole sequence. Then you will take the higher V by S ratio, not for the movement, but for the sequence. Clear? Okay. So I will take 0.39 from here, and then I will take 0.09 from here, and I will take 0.23 from here. Okay. Now total is 0.71. Okay. So doing this was good or bad? How do you know?
Good, because there is a...
Because V by S ratio has decreased. Clear?
Also on north sound we take.
We can do this. We can do this.
Or only.
No, we can do this. Okay? We can do this in the north-south as well. But north-south, the requirement is not so much here, because they are already very close to each other. Okay? Here it was more required. Okay? But as I mentioned earlier, if you get V by S ratio 0.85, 0.8, something like this, okay, even if you don't do any other improvement, this is still acceptable. This is still allowable. Okay, but you cannot leave it like this. So you made the first timing plan. Obviously, the demand will change, right? Every intersection will have its own demand, own lane width, and own saturation flow rate. Okay. So, for example, you did it for another intersection. When you made the first phasing plan, even after doing the combination and merging, you are getting V by S ratio 0.9, 0.95. This will be very difficult to design. Okay, so V by S ratio should be as low as possible. The design will become better. Okay, that's why we discuss these things. Okay, so we discussed two principles here basically. First one was they went with the easiest approach, which is each lane group has a phase. Then you do the summation, simple summation, and you get this one. Okay, if it is practical, fine, could be. You can stop here, no problem. If not, the second easiest approach is every direction has a phase. All movements in that direction together. Okay, left turning straight together, left turning straight together. Okay, you do the V by S ratio. It's this much here, but it could be anywhere. Okay. Next thing you can do is try to combine the movements which have what? What is the difference between this one and this one? Similar V by S ratios. Okay. Look at the movements which have similar V by S ratios and put them in the same phase, even if they are from different directions, provided that they are not conflicting. Okay. If they are conflicting, you cannot merge. Okay. And then what did we do here? What is the difference between this one and this one?
Extend.
We extended the movement which required more time. Okay. We extended into another phase. This one. Clear? Okay. So this can be done as well. Why did we extend it? Because we looked at the combination and we found that they have still a lot of difference in them. Okay. I already tried putting the other movements together. So I don't want to disturb this. What can I do? Okay, let me just extend it. Keep the same combination, but just extend it. Clear? Okay. Okay. Think of. Okay. The next step is to find out the yellow and all red time. Okay. Yellow and all red time is calculated from these equations. Okay. I need the perception reaction time. It's a standard. Okay. For signal it is taken as 1 second. For signals it is 1 second. Speed is the speed of the road. Okay. Should be given or you will observe it. Whatever. Okay. Standard deceleration. No. Deceleration, not gravity. Okay. Standard A, not G. A. Okay. This one. Okay. 32.2 is this one, right? This is gradient of the road. Okay. What else do we need? Yeah. W. W is the width of the intersection. Okay. L is the length of the vehicle. Length of the vehicle, standard car is around 20 feet. Okay, 20 or 20. Okay, so and S naught is the speed of the road. Okay, so what are we doing here? For example, so the main thing is W. Okay, the W. Okay, speed. If I am doing it for this road, I will take the speed of this road. I am doing it for this road, I will take the speed of the other. Okay. How will I calculate W? So if I am doing it for this road, okay, or the east-west road, okay, my W is what? From here to here, right? Okay. So how many lanes I have? 3 lanes. Okay. Each lane is how much? 12 feet. And then I have a median as well. The median is 5. So what is the W for this direction?
12 times 3
plus 5. Okay, which is 41. Clear? Okay, and what about this one? I have how many lanes now? 5 lanes. Okay, so 12 into 5 plus 5. Okay, 65. Which is 65. Clear or not? Okay, so this is how we get the W. You have to look at the intersection geometry. How many lanes are there? If they are the median, what is the, and there is no shoulder here. Remember, you can have shoulders as well. You have to add it. Clear? Okay.
Again.
From where?
The W.
W is from this side to the other side. Okay. So how many lanes you have from here to here? 1, 2, 3, 4, 5. 5 lanes. Okay, each lane in this case 12 feet. Okay, so 12 into 5 plus 5 feet of median. Okay, so this will be the W for this road, north south. Okay, for east west again you will do the same thing. Okay, and the thing which I was mentioning was, in this example there are no shoulders. If I say there is a shoulder as well, you have to add that one as well. Shoulder will be here, right? Shoulder will be on the road. Okay, so you have to add that one as well. So you have to look from one side to the other side, how many lanes you have, median, shoulder, everything, you will add it. Clear? This is your W. This is how you get W. Okay? And for each, you can see each direction has a different W. So each direction will have its own all red time and yellow time. Okay? Not yellow. Yellow can, I think yellow is the same. Yellow, yeah. Yellow, there is no change in yellow. Okay? So if yellow only changes according to what? Speed. Okay? So if both roads have different speed, then the yellow time will be different. Otherwise, for both roads, the yellow time will be same. Okay? And the all red time, this is the all red time. Okay? So this changes according to speed and the road dimension. Okay? So it will change. Because of the dimension of the road, it will change. Clear or not? Okay? Can I have it different for east and west? For east and west, can it be different? No? Never? Never?
There is a ramp.
There's a ramp? Or what?
Example from there.
Can I have a different yellow for east direction and the west direction? Can I have this? No? Never? Yellow changes according to what? Speed. Can it happen that east direction has different speed, west direction has different speed? Can happen, right? It can happen. It can happen. Theoretically, it can happen. Yeah, we don't prefer it, but it can happen. Okay, so anyways. So these values are calculated for the intersection we have, and this is what they are getting. Okay, like I said, perception reaction time plus the first ratio plus the second ratio with the W. Okay, this is for the east-west road. If I'm doing it for the east-west road, I took the W in this direction. And this is for the north-south road, so I took the W in the other direction. Okay, these two values combined are yellow. This value is my all red. Okay, so it was 3.9, they made it 4. If it is 3.1, then
3.4.
yeah. 3.9 they made it 4. 3.1 they make it
3.5?
3.5, yeah, it can do it. But not 3.
No.
Okay, not 3. Okay. 0.92 again 1. Even for 0.92 you can give 1.5, but you cannot make it 0.5. Got it? Okay. Round up. So for east-west direction, this is the yellow, this is the all red. For north-south direction, this is the yellow, this is the all red. Okay. Now, for lost times, they said it ranges from 3 to 4 seconds. Okay, we have already discussed it, how to find out, but they gave us some values which we can use. So, each phase can have a lost time between 3 to 4 seconds. Okay, so they are taking, and each lost time has 2 parts: startup lost time and clearance lost time. Okay, so they are saying we will take each part as 2 seconds. Okay, so 2 seconds for this one, 2 seconds for this one, total is 4. Okay, now if I go back, this is my final plan, right? Huh? This is my final plan. How many phases I have? 4 or 8? 8?
4.
4 phases. Why 4? Yeah, 8.
2.
Oh, no, 4
Oh, no.
The others two together, 2 together.
Yeah. Okay, overlapping we won't count.
Yeah.
Okay, listen. Okay, so L1, L2, both 2 seconds, total 4 for each phase. And we have then, discounting the overlapping phases, we have 4 phases. Okay, so 4 into 4, total lost time 60 seconds. Okay, then what is XC? XC is my volume to capacity ratio. XC is my volume to capacity ratio. We decided. Okay, there is a range given. Okay, I believe it starts from 0.8, goes up to 0.95. Okay, we decide how much do we want in this range. Too low, if you decide it to be too low, the design will be overestimated. You may have a very, very long cycle length. If it is too high means what? How much? How much?
Above 1?
Huh?
Above 1?
Can I take above 1?
No.
We cannot. Okay, so too high can go up to what?
Give us 1.9 something.
Okay, maybe 0.9, maybe 1. Okay, but that is also not good. Okay, 1 or close to 1 means what? Your capacity and volume is exactly or almost equal, which is not good. Okay, we want capacity to be higher. Okay, so but we are doing the design, so I don't know the actual value right now. The actual value could be more than 1, right? The actual value could be more than 1, but right now I'm doing the design, so I try to keep it less than 1, right? So we have to select a value between 0.8 to 0.95 they have here. Okay. In this case, they have selected 0.9. It's a selection. It's a selection. Okay. But you have to keep one thing in mind, which is your summation of V by S ratio. Okay. So for example, if I stopped here, so my summation is 0.86. Okay. Then I cannot select a V by S V by C ratio of 0.85. Okay, or even 0.9. Okay, my V by C ratio should be higher than my final summation of V by S.
By how much?
Huh?
By how much? Higher by how much?
There is no value, you have to look at it. Okay, but we try to keep it as high as possible. The difference should be higher. Okay, we had an example. We kept it like it was 0.89, and then we took the XC value 0.9. So the difference was only 0.01. Okay, and the cycle length was going in hundreds and thousands something. Okay, and to make the matters interesting, it happened in the exam. So that's why I'm saying. Okay, so like it happened with you guys, right? It happened with you guys in the exam, right?
Jason.
I'm not talking to you. Other people who knew what was happening. Okay? You get the point, okay? You have to select the V by C ratio. You were asking me, doctor, what do you want? Huh? What checks do you want? Okay.
From the question.
And he asked me in the last 5 minutes, huh? Okay.
I just hear it though.
Yeah.
I already.
Very good.
Later.
I have the marks. Okay. What was my point?
ركز قدام بقى ركز تطلع على دويك الحين.
Stay at the front. What is wrong with you? Focus on your coffee. Okay. What was my point here? XC should be what? V by C ratio should be what?
Higher by difference.
Higher by what? Higher from what?
From V by C.
From summation of V by S ratio. Okay. And more the difference is better for the design. Okay. To get some practical value. Okay. From where did we get the cycle length? Okay. So we have two values for the cycle length. Okay. XC is the one which we selected. Okay. We selected to be 0.9 in this case. Okay. Because our summation V by S is 0.7 something. So a lot of difference. No problem. So 0.9 this one. This is total lost time. Lost time of one phase 4 seconds. Lost time for 4 phases 16 seconds. So this is 16. Okay. What else do we have? Summation V by S ratio, which we have from the phase diagram. Okay, it is 71, right? 0.71 something. Okay, so this is one equation. Okay, and this is another equation from Webster. Okay, we can use this one as well. They use both of them. Okay, so this one again lost time, this one summation V bias. There's nothing new here. Okay, the equation is different, but there is nothing new here. Okay, the values which they got are these values. This is from the normal equation, this is from the Webster's equation. Okay, you can see that Webster's equation gave a higher answer. Okay, so now we will, I think they rounded off to 65 and 100. Okay, they rounded this one off to 65 and this one to 100. Okay, after we do this, we'll calculate the total effective green time we have. Okay, after you find the cycle length, we'll calculate the total effective green time. Okay, so how do we do this? You have the cycle length after rounding off. So this one became 65, right? This one is 65. What is my lost time? 60. So total effective green time is 65 minus 60. Okay. For this one was 90. Okay. So 90 minus again lost time will not change obviously. So 90 minus. Okay. I think I mean this is other way. I'm sorry. 70 and 85. Sorry. So 70 minus 16 total effective green time, and 85 minus 16 total effective green time. Okay, because these values are from different equations, that's why. Okay, clear? Yes.
I think the 80 and 100 second is the cycle.
Which one? They already do. Sorry. Cycle length is this. Okay. So 75.8 and the other one was already 100. Okay, good. So these are the effective green times. Okay, sorry. So these are the cycle lengths from those equations. This one was 75.8 rounded off to 80. So 80 minus 16, 64. The other equation, the Webster's equation, gave 100. 100 minus 16, 84. Okay, so these are the effective green times, total effective green times. Now I have to calculate the effective green time for every phase. For every phase. I will go to the phases now. Okay. So I will calculate. Now I am dealing with each phase separately. I am dealing with each phase separately. So I will calculate the effective green time for each phase separately. How do we do this? We know the total, right? Total is, let me take the other value. So total is 84. Okay, total effective green time is 84. I have to divide this 84 into these movements. Okay, 85 must be divided into these movements. Okay, now which movement should receive higher value of time? The one which has higher what? V bias. Okay, so we take the, so if you want, for example, for the first movement, this one, it has V bias ratio of 0.19. Okay, so let me call it G1. They are using their own term, but okay. So G1 equals to what? Total green time I have is 84. The V bias ratio for this movement is 0.19, and the total is 0.71. Okay, the total green you have multiply by the ratio of V bias ratio of that movement to the total.
22.1.
Okay, this is how we will do for all these movements. Okay, each time what will change? The V bias ratio. Obviously total green will not change and total V bias will not change. Okay, so you will just replace the V bias ratios of that movement and you will calculate the effective green time. Clear? Okay. Okay. Now, what is happening here? Some of the movements are happening together, right? They are happening together. Okay, we did not consider this, that they will be overlapping. Okay, So now after you calculated the effective green time, you will consider the overlapping. I think there's a table, yes. Okay, effective green time using the smaller cycle length, effective green time using the other cycle length. Okay, but the method is same. Okay, to take total green time, multiply by V bias ratio divided by total V bias ratio. Okay, so now the movements which you see in bold color are those which are critical, which the one which we took for the design, the one which we took in the summation of V bias ratio. The higher one, yes, the higher one. Okay, so we took which movements? These two, then any one of them, and then this one. Okay, so these are the movements which are taken in the calculation, which are taken for design, right? Others are happening at the same time. Okay, let us take these two. I did the design for this one, right? So my signal timing is according to this movement. Okay, this one is happening together. Okay, now what will happen? I calculated the phase time according to this. I put 0.23 here. Okay, and then I calculated for this. I put 0.19 here. Okay, obviously the green time for this one is higher. The green time for this one is higher. The green time for this one is less. Okay, but can I do it in the field? I cannot give more and less because they are one phase. Okay, they are one phase, right? They are parallel. Like they are different phases, but they are parallel. Okay, so what will I do? Should I make this smaller or this one bigger?
This one bigger.
Okay, you have to give extra time to this one so that it can close with this one. Okay, so if I already calculated the time here. Okay, where was it? North, right? We're discussing what? North or south? Straight north and okay. So not southbound through, and where is northbound? This one. Okay, this one gave me 0.27. This one gave me 17. Okay, not 20.7. Sorry, 20.7. And this one gave me only 17. Okay, so according to this, what will happen? This will remain open for 20 seconds and they should close in 17 seconds. I cannot do this. I made them parallel. Okay, so this one should also close in 20.7. Got it? Okay, so after you calculated the green time using that equation, then you have to see which movements are happening parallel. Okay, and you see where are you having extra time between parallel movements. That extra time must be added to the other movement as well. Got it? Clear? Okay, the same thing will happen for this sequence as well. And what did I say here about this thing? So here I was comparing between this movement and this movement, right? Here I am comparing between what? The sequence. So you will look at this sequence, time of this sequence. Obviously this one will be higher and this one will be less. Okay, so this sequence, now this is what now, westbound left and eastbound through. Where is westbound left? Westbound left, eastbound through. Okay, total is how much? How much is the total? 35.1. Okay, and the other two, westbound through and eastbound left, their total is how much? 32.4. So 35.1 and 32.4, they are happening parallel. Okay, this and this, they are happening parallel. So I have to make their time equal. So this summation should also be 35.1. But I have two movements here. I have to add something, right? Should I add it here? Should I add it here? Should I add them equally? Okay. For the sake of signal design, it will not matter. You say, okay, I will add it here because this one is higher. So it's a bigger movement. Let me add it here. All 3 seconds, add it here. Or all 3 seconds, add here because this is already lower, and so on and so forth. Or add equally 1.5 there, 1.5. No problem with that. Okay, because I am just trying to adjust the timing for the sake of practical reasons. Traffic is already satisfied. Okay, so, but they are saying the common practice is we add it in the through movement only. Okay, so they will add it in the through movement. Okay, so with the 3 seconds extra, it will become 18 seconds. Clear? Okay. You have to make them equal. This is what you have to do. Okay. Whether you make them equal by dividing the time equally, extra time equally, or putting in one movement or the other movement, doesn't matter. Here they are saying we prefer to add it in the through movement. Clear? Clear? Any questions? Okay. So these are now my final green times. These are effective green times. Which ones? Effective green time. Now what is an effective green time? Effective green time is time of one phase minus lost time. Time of one phase minus lost time. What is one phase?
Green, yellow.
Green, yellow and all red. Okay. So green, yellow, all red minus lost time is this value. Green, yellow, all red minus lost time is this value. Now which of these values you know? Do you know green? No. This is effective green, not the green light. Do you know the green? We don't know. We know yellow. We have calculated.
Yellow and the all red.
Okay. Yellow we know. All red we know. Lost time we know. So only thing remaining is the effective, the green time. Okay. Okay. So I'll put effective green equals to green plus yellow plus all red minus lost time. Okay. So I will take the small g's from here. Okay. Y and AR already calculated, TL already assumed. Okay. So you will get what? Green. And keep in mind yellow and all red is different for each direction. For east west is this different and north south is different. Okay. Lost time is 4 in all cases and small g from this table. Clear? Okay. So you will take the capital G for each movement. These are now the green light timings. Okay, so these are the green light times. So the signal will be green for this movement for 16.1 seconds. Then it will turn to yellow. Okay, for I think it's 4 seconds, and then it will turn to all red, which is 1 second. Clear? Or 3 seconds, sorry. 3 seconds yellow and 1 second all red. Clear? Okay, so now we know all the 3 timings of the signal. We know the total cycle length of the signal. The design is done. Okay, next time we will discuss the pedestrian check. Okay, we'll discuss the pedestrian check.